starting my recording. Okay. Now, I welcome you to the week 4 live interactive session for the course Polymers, Concepts, Properties, Uses, and Sustainability. Now, let's get on to the session. You're able to see my screen, right?
Yes, ma'am.
Okay, fine. So, as usual, we'll go through the brief recap of lectures of week 4. So, week 4 was on polymeric materials of different kinds. So, this week's lecture started with glass transition, which is on properties. So, this was in continuation with the glass transition lecture of the previous week. Okay. So, in this lecture, the concept of segmental relaxation was discussed first, right? Paul, can you just mute your
Sure, ma'am.
yeah, because I'm getting some feedback. Yeah. So, a segmental relaxation was discussed, and what is instantaneous relaxation? First of all, the relaxation time, instantaneous relaxation, and when in which case there is no relaxation, and the activated process in case of relaxation time, and what is a cooperative process. So, this was discussed, and then the free volume theory was introduced, and with this understanding, the William Landau Ferry equation was discussed. So, and uh, further, it was also discussed that the William Landau Ferry equation is also sometimes, in certain literature, it is described as Vogel-Fulcher equation, right? And then how the Arrhenius and WLF different, dependence, vary, right? So that was also discussed, and then other transition in addition to your uh the segmental relaxation, the different other transitions were also discussed, correct? So what were the other transitions that were discussed? Do you remember? Now you can unmute.
Um, they discussed stretch exponential rate.
Stretched exponential
Uh,
rate is your cooperative process,
yeah.
correct? uh,
Yes, ma'am.
yeah, I'm asking what were the other transition other than your glass transition that was discussed?
I don't remember.
Okay, okay. So there were other transitions like beta and gamma transition, that were discussed. So these were other transitions. Uh, and then lecture 24 was on states in environment. So this was a sustainability based lecture. So what is the global and long term impact, overall impact, and impact on environment of polymers, and then what is the biogeochemical cycle was discussed, and what is the role of polymer in the biogeochemical cycle was discussed, and then nitrogen cycle was discussed in detail, where about the nitrogen sources, natural sources, and anthropogenic sources were discussed, and what are the states in environment in which the polymers uh, interact with. So they interact with water, soil, and air, right? And their impact was also discussed. Next, in the lecture 25, liquid crystalline polymers were discussed. So what is a liquid crystal, right? And what are the different liquid crystalline polymers? What is the free energy exchange associated with liquid crystalline polymers was discussed. And then there was a discussion on liquid crystalline polyesters and a comparison between liquid crystalline polyester and polyethylene terephthalate, right? and how the properties and all differed when it was in a when it was a liquid crystalline PET versus a normal PET. And then the final discussion was on Kevlar. Then lecture 26 started with copolymers. It was on concepts. So first an introduction of what is a homopolymer and a copolymer was given, and how the sequence distribution varies in case of copolymer. Different kind of sequence distribution was discussed, and how polyethylene can be a copolymer was discussed, right? So, ethylene along with some other, monomers, right? Butene and all, you could still form a polyethylene copolymer. But still, you don't really find a difference as a molecule because the repeat units are same. Correct? Hello?
Yes, ma'am. This is
Yeah.
CH2 and CH2.
Yes, yes, yes. So, different olefins can be used. But since you don't visually see, you don't see the repeat unit difference, you cannot really say it's a copolymer, but you can still form copolymer. Okay, and then there was a discussion on silicon polyether. Finally, there was a discussion on chitosan and chitin. Right? How is chitosan formed from chitin? There is some modification that happens that change to formation of chitosan from chitin. So this was also discussed. Next, lecture 27, it was again on copolymers. Here, the properties of copolymers was discussed. So, how does the controlled copolymerization for specific copolymer takes place, right? How do you define the reactivity ratios and copolymers related to homopolymers? And then graft and block copolymers were all discussed in this lecture. You're able to hear me clearly, right?
Yes, ma'am.
Okay,
Okay.
because there is some construction work going on, so I just want to ensure if I'm audible properly.
Yeah, you can hear.
Yeah. And the last two lectures of the week were on blends. Before the lecture 28 was on blends, which was on concepts. So mixtures of polymer. Now how do you form blends? Like it can be melt blending or solution blending, right? And then a reactive blending as well. And then miscibility in polymeric systems. In which case you have a miscible polymer and when does it become immiscible? Uh, right, mixtures of A and B, and then polymer solvent miscibility were all discussed. The final lecture was on blends, which was on properties. So here Gibbs free energy change due to mixing. This was discussed, and then Fleury-Huggins theory was introduced, and polymer blend phase separation. How does phase separation happens in case of polymer blends? Uh, okay, and the critical temperature of phase separation, and finally the TG of miscible polymer blends was discussed. Correct. So in TG of miscible polymer blends, what equation was discussed? Do you remember? In fact, we solved one problem last week in lecture, session itself on that equation.
Yes, ma'am. It was Flory Fox.
Yes, yes, perfect. So Flory-Fox equation. So that's it with the recap of lectures. So you were able to, recollect whatever you went through. You have any specific doubts in the lecture?
Ma'am, I have one doubt in WLF relation.
Okay, yeah.
Uh, there was one constant alpha in the
Yeah, yeah, yeah.
equation.
Yeah, 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 yeah. So, you want to know what was that? It is some constant alpha. The main, concept that you have to. I'll let you know what is that. Maybe in the through forum I'll reply, or because I don't remember. Sorry. But the main thing
It's
in the
okay.
WLF equation is your uh, what is it? your fictitious temperature, that is T minus, sorry, Tg minus that T minus T infinity, which comes to becomes C2, which is nothing but approximately 50 degrees. That is 50 degree below your glass transition temperature. So that is what is your key in that equation. Okay.
Okay, ma'am.
Yeah. Yeah. Mm. I'll just check and let you know what is that alpha. I don't remember it.
Sure, ma'am.
Yeah. Okay. Now let's go on to the practice assignment session. So any other doubts you had, or that was the only thing?
No other doubts.
Oh, okay,
Okay.
fine. Yeah. Okay. Now let's go on to the practice assignment. So the first question is: perfect energy storage corresponds to uh, relaxation time tends to 0, no relaxation. Relaxation time tends to infinity, instantaneous relaxation, or relaxation time tends to 0, instantaneous relaxation, or relaxation time tends to infinity, no relaxation. Which one of these corresponds to perfect energy storage?
Lambda tends to infinity.
Okay, lambda tends to infinity, and
No relaxation.
okay, yes, lambda tends to infinity. That means no relaxation. It takes infinitely long time for the material to relax. That can be approximated as no relaxation. So that means if there is no relaxation, there is a perfect storage of energy, because your relaxation basically corresponds to your dissipation, right? Dissipation of energy, right? So if there is
Yes,
no
ma'am.
dissipation of energy, obviously the energy is getting completely stored. Okay. Yeah. And then the next question is: free volume reaches a lower threshold, leading to cessation of segmental mobility in rubbery state. Is it true or false?
True.
So free volume reaches a lower threshold, leading to cessation of segmental mobility in rubbery state. Is true, you're saying?
Yes, ma'am.
Is it so?
Then it will be the segmental mobility won't be possible.
Okay, but in which state is it?
It will be in glassy state.
But what is the question?
Mm. Leading to rubber. Ma'am, I didn't get you what you meant.
So you said there is a cessation of segmental mobility in glassy state, right?
Yes, ma'am.
Hmm. So is this statement true or false? Now, whatever statement is given, free volume reaches a lower threshold, leading to cessation of segmental mobility in rubbery state. Is it true?
It's true.
How can it be true? It's false. Your free volume reaches a lower threshold, leading to cessation of segmental mobility at glass transition.
Yeah.
Right? Only in glassy
Okay,
state,
okay,
your
okay.
segmental mobility
Now I got it.
is, yeah, the free volume reaches a very minimal value. So there is no segmental mobility possible. The segmental mobility is completely arrested in glassy state or in glass transition. And it's not in rubbery state. Rubbery state, you have segmental mobility. That means there is quite a bit, more free volume. Right? It is not in the lower threshold, but it is higher value in rubbery state. Okay?
Now I got
Yeah. Next. Long distance transport of plastics in water is possible due to. So
it. Ma'am,
you could
are there
see
any options? Or
what
is it not
happens.
the?
What happens, if you see, you could see, plastics floating on water, right? And it is being transported to long distances, right?
Yes, ma'am.
So why is it so?
because the density is almost same. Oh,
Yes. So it is having the density in of plastics are and water are very similar. That is why otherwise not it will sink down, right? There will not be transport. Only in that particular place there will be accumulation because it sinks down in the water body. But since the density is very less, it gets transported to a longer distance. Okay.
okay, ma'am.
Yeah. Next, overall impact of polymers is assessed based on
Overall availability. I don't know. Just a guess.
okay. Okay. It is actually the impact of polymer is based on its life cycle assessment. Okay. And then biogeochemical analysis and ecosystem analysis. So in all these three area, what is the impact of the polymer will give the overall impact of the polymer. Okay. Uh, how is it playing role in the biogeochemical cycle, whether it is getting into the biogeochemical cycle or how is it affecting in the ecosystem, and what is how does the life cycle also, because there are energy associated and other issues associated with the polymers and all. So the entire life cycle is to be assessed also. So this gives the overall impact of polymer. uh, okay. The next question, styrene, butadiene styrene is an example of,
Uh, Tri-block copolymer.
yeah, it's a triblock copolymer.
Mm.
Okay. Now let's get on to next question. So identify and match the copolymers. So there are four figures that are given and four options given: gradient copolymer, periodic, graft, and aperiodic. So which one corresponds to what?
Uh, A is graph.
Okay.
Second one is gradient.
Second one
Then
is gradient, you're
third
saying.
one is periodic. And fourth one is aperiodic.
Second one is gradient, you're saying.
Yes,
And
ma'am.
okay, and third one you're saying
Periodic.
periodic. Okay. And
And fourth
fourth one
one aperiodic.
aperiodic. Is it?
I don't remember exactly. Just
Okay. So it is actually your uh, the figure C, it is periodic because the polymers are let's say orange one and your uh, red one are coming periodically, two orange and one red. Whereas so first one is graft, as you said, it is grafted on the other polymer is one polymer is grafted on the along with the main chain of the other polymer, so it is a graft. And your option B, this is actually aperiodic because you have one orange, three red, again one orange, one red, and again one orange, four red, and then two orange. There is no periodicity. Suddenly there is one, there is three, there is one, and then there comes two oranges. Whereas there are three red one, and then suddenly one, and then again it goes to four. So it is aperiodic. There is no periodicity. Okay. And
okay, ma'am.
as I said, C is periodic. and D is actually gradient, because if you see orange, it is initially 3 3 and then 2 1. So there is a fall in the gradient in orange, whereas in case of red it is 1 2 3 4, right? So
Okay.
there is a gradient. Okay.
Okay, ma'am. Got it.
Yeah. Now next, changes in property due to subsegmental relaxations are dash compared to that of changes due to alpha transition. Is it higher or lower, or is it same level, or none of the above? So property change due to subsegmental relaxation are dash compared to that of alpha transition. So first, do you remember what is alpha transition?
No, ma'am. I don't remember.
Okay. Okay, just answer me. Okay, you don't remember
So I will
what is alpha transition. First of all, alpha
go
transition
with lower.
lower. You're saying. Why do you say lower?
Just a random guess.
Random guess. Okay. First of all, your alpha transition is nothing but your glass transition, which is nothing but your segmental relaxation. Okay. So
Okay.
your answer is correct. Lower. So this is your segmental relaxation. So this is the case for PMMA, polymethyl methacrylate. Okay, your glass transition is your alpha transition, whereas your beta transition are some kind of side groups and other groups, transition. Okay, rotations. For example, here
Okay,
in
ma'am.
case of methacrylate, your beta transition, it corresponds to your methacrylate group rotation, and then your gamma transition, it corresponds to your methyl group rotation. Okay. So you could see that this is a specific volume and this is temperature. So as the system moves from gamma transition to beta transition, the changes are less. Okay, the slope changes very less from gamma to beta, right? As the
Oh, yes,
temperature
ma'am.
increases. Whereas when it crosses the alpha transition, that is the glass transition temperature, there is a orders of magnitude. There is a higher slope. That means there is an increase which is comparatively higher than the subsegmental transition relaxations. Okay. So as you
Okay, ma'am.
increase the temperature from the completely, very low temperature, as you increase this temperature, slowly subsegment starts, relaxing, or it starts rotating, and then so that again depends on the bulkiness of the those subsegments. For example, here uh, from 40 to when it goes to around minus 40 to around minus sorry, to plus 30, you can see that the methyl group starts there is a methyl group rotation, and then beyond 30 degrees there is a methacrylate group rotation, and finally beyond around over 100 degrees, you could see that the segmental motion happens. Okay. Hope you're clear, right?
Yeah.
Okay. Okay. Now next question. Hydrophobic chitin is converted to hydrophilic chitosan by replacement of, is it done by replacement of hydroxyl group to acetylamine group, or acetylamine group to hydroxyl group, or acetylamine group to amine group, or amine group to acetylamine group?
Acetylamine to amine.
You're saying acetylamine to amine. Okay, let's see. Yes, it is acetylamine to amine group. So this is chitin. So it has NHCOCH3. And in case of chitosan, this gets converted to NH2. You're able to see it, right? Amine group.
Yes, ma'am.
Yeah. Next, in case of random copolymer containing monomer M1 and M2, where M1 has the ability to crystallize when it polymerizes alone. Okay, the crystallization of M1 in copolymer is possible under the condition, under which condition is crystallization of M1 possible in the copolymer. So there is some random copolymer having two monomers M1 and M2. So if you consider a polymer of only M1, it can crystallize alone. But in case of copolymer of M1 and M2, under which condition there will be a possibility of crystallization of M1. You're able to get the question, right?
Mm. Yes, ma'am.
Okay.
Like separation of M1 and M2.
Okay. So that is what is needed for crystallization of M1 in the copolymer, is it?
Yes, ma'am. Separation of M1 from M2.
Okay. Okay. So you're right. Actually, the answer is cooling the random copolymer from melt state. You have to cool it down. So in that process, there should be a demixing of M1 and M2, and then M2 should be excluded from the lamella of M1. Then only M1 will crystallize.
Okay.
Okay.
Okay. So there are two reasons.
Yes. First, M1 and M2 should demix during the cooling process. As you said, it should separate. And then in the lamella also, no, for the crystallization to continue, M2 should not interfere with the lamella. It should be excluded from the lamella. Then only crystallization will be possible. Okay.
Okay, ma'am.
Yeah.
Got it.
Yeah. And then one more thing, you asked on this WLF equation, right? It's actually an empirical equation. So this alpha and there was one more term called B or beta that was mentioned, right? So these are all empirical constants. Okay, and that is why you end up with C1 and C2. And C2, it would have been discussed in the lecture that C2 comes to, in certain polymers, it comes to 33, certain polymers 55, certain polymers 50. These are all based on experiments where you arrive at the C1 and C2 value, and C2 value approximately comes to around 50. Okay.
Okay.
Okay, so that is nothing
So
but your
it's a constant.
empirical
Okay.
constant. Yeah.
Okay.
Yeah. And then the next question. Given below is the expression for Flory-Huggins theory of mixing of polymer A and B. Identify from this expression how entropic contribution in case of mixing of macromolecules is minimal. So you're able to understand the question. So they have given the Flory-Huggins theory expression of mixing of polymer A and B. Now you have to say how is the entropic contribution minimum from this expression. Identify why the entropic contribution is minimum based on the expression.
The chi phi A phi B is the enthalpic part. Rest all is the entropic part.
Okay. So you're saying chi phi A phi B is the enthalpic part, the rest is entropic part. Yes, okay, fine. So why is this the value of this part is very low?
Because the volume fraction is very low. It is between like maximum 1.
Okay. It is between 0 and 1, you're saying, volume fraction. What is the other thing that is present that can make it low? Because if you, yeah, that can make it low.
I have no idea.
It's nothing but your Na and Nb. These denotes degree of polymerization. So degree of polymerization will be high, right? And as you said, phi A and phi B are volume fractions. So logarithm of phi A and phi B will be very small values. Okay. So combination of these two, uh, makes the entropic contribution to be very small. You're able to figure out this denominator value is large. That means the overall value, if the denominator is large, the overall value will be very small, right? Also, as you
Okay.
said, the
Oh,
numerator is, because this is the degree of
yeah.
polymerization, right?
Yes, ma'am.
Yeah.
Uh,
And this is nothing but a fraction, and this is logarithm rhythm of some fraction. So logarithm of a fraction, a value 0 to 1 will be smaller value, very small value. And here the denominator is also large. So that means the overall this value will be very small, right? That makes it exceedingly small. Okay.
okay. Okay, ma'am. Got it.
Next. For a polymeric system of A and B having lower critical solution temperature, as we increase the temperature for the same volume fractions of A and B, this polymer system becomes miscible from partial miscible system, or becomes partially miscible from miscible system, or partially miscible in both the cases, or miscible in both the cases. What happens?
Becomes partially miscible from miscible.
Okay, you're saying it becomes partially miscible from miscible. Okay. Yes, it becomes partially miscible from miscible. So lower critical solution temperature means it is the minimum temperature below which the system is completely miscible. Okay, this value, the system is completely miscible, and as you increase the temperature, the system starts becoming partially miscible. Okay. Okay.
Okay,
Now,
ma'am. Got it.
now let's proceed to the next question. If we bring down the temperature of a polymer blend or polymer solution with upper critical solution temperature suddenly, then we get a dash decomposition. What kind of decomposition happens when we bring down the temperature of a polymer blend or polymer solution with upper critical solution temperature?
No idea.
Okay. Uh, you start getting a spinodal decomposition with co-continuous phase separation. So this is a system having upper critical solution temperature. So temperature versus volume fraction. So in case of upper critical solution temperature, above the critical solution temperature, the system is completely miscible. So as you bring down this temperature, okay, there are two kinds of decomposition generally possible in these kind of, whether it is lower critical solution or upper critical solution. One is spinodal and the other one is binodal. Okay. So this green curve denotes the spinodal decomposition, and this one it's binodal. Okay, if you bring down the solutions temperature suddenly, if there is a sudden drop, what happens is that it gets into the spinodal decomposition zone. In this zone, what happens is that the phase separation, it starts like suddenly with a co-continuous phase separation. Whereas when the temperature is brought down slowly and it enters the regime of binodal decomposition, what happens in the case is that there will be a nucleation and growth. So slowly the nucleus starts forming, the separation of the phases starts forming, and it develops. Okay, you're able to get
So
it?
will it crystallize?
No, it's not about crystallization. It's about the phase separation. Nucleation here means that the separation starts the phase in, because in this region of above the upper critical solution temperature, the system is complete, the blend is completely miscible. Okay, it forms a single system. Whereas here it starts separating, it starts phase separating. So A starts separating from B, so small uh, patches of A starts forming if it is a binodal decomposition. Okay, and then this starts increasing in size. Okay, it doesn't mean that there is a crystallization and all. It is
Okay,
it is more with the phase separation. Okay.
got it.
Yeah. The next question. The amount of low molecular weight plasticizer with a TG of minus 60 that must be added to nylon 6 to reduce its glass transition from 50 to 30 degrees is. So, what is the quantity of some low molecular weight plasticizer having a glass transition temperature of minus 60 that must be added to nylon to reduce its glass transition from 50 to 30 degrees? This is the GATE 2022 question. So, how do you start about this?
Ma'am, but we need a blend, right? For what is the glass transition for nylon 6?
Glass transition temperature of nylon initial glass transition is 50 degrees. Okay. And then upon addition of this low molecular weight plasticizer, it reduces to 30 degrees.
Okay, so we are adding the plasticizer to nylon 6.
Yes, we are adding the
Okay,
plasticizer to nylon 6 to bring down its glass transition temperature so that we increase its flexibility. So even above 30 degrees itself, nylon is flexible. In the current scenario, without the plasticizer, the nylon is flexible above 50 degrees only. Below 50 degrees, it is, it's not flexible. It's rigid. So how do you find the uh, sorry, the weight fraction or weight of the plasticizer that is to be added? What equation should be used?
or EFOX.
Yes. So given TG of plasticizer is minus 60, TG of nylon is 50, TG of nylon after plasticizer addition is 30 degrees. So what is the weight fraction of the plasticizer? So again, you have to use Fleury-Fox equation for this case also. If you are adding some low molecular weight plasticizer also, you can use the Fleury-Fox equation. So you have the Fleury-Fox equation 1 by Tg uh, of the system containing nylon and plasticizer is equal to weight fraction of plasticizer divided by glass transition of plasticizer plus weight fraction of nylon by glass transition of nylon. So we can, since there are only two systems, we can replace the weight fraction of nylon by weight fraction of plasticizer, because Wp plus Wn is equal to 1. So Wn is equal to 1 minus Wp. So that is what is given in this. So now you have all other terms except Wp. Now can you find Wp and say what is the value of Wp?
Ma'am, do we have to convert it to Kelvin, the temperature?
I don't know, you have to say me. We solved a similar problem last week.
Uh, Wait, ma'am, let me check.
And
Oh, yes, ma'am. Yes, we have to convert. Sorry, ma'am.
no
I just
problem.
got confused.
No problem. This Fleury-Fox equation is based on temperature in Kelvin. So you have to convert the temperatures to Kelvin and then solve the equation. Now solve the equation and tell me what is the solution. Able to calculate?
Yes, ma'am. I'm doing.
Okay.
Ma'am,
Yeah.
I got WPS 0.1278.
0.1278. Okay. Now you have to convert it into percentage. That means,
It will be 12.78%.
okay, let's see what is the answer. Yes. You said you have to convert the temperatures to Kelvin. That's what is done. So you are right. So first, converting the temperature to Kelvin. So uh, the final glass transition of nylon with plasticizer is 30 plus 273. So it will be 1 by 30 plus 273 is equal to WP by minus 60 plus 273 plus 1 minus WP by glass transition of nylon is 50 plus 273. So that you will end up with 1 by 303 equal to WP by 213 plus 1 minus WP by 323. So when you do the mathematics, you will get what is WP as 0.1278. So converting into percentage, the amount of plasticizer to be added is 12.78% to reduce nylon's glass transition from 50 to 30 degrees. Okay, let's move on to the
Okay, ma'am.
next question. Polyvinyl chloride has higher glass transition than polypropylene due to the presence of bulky side group, polar interactions, restriction of bond rotation, non-polar interaction. What makes polyvinyl chloride PVC to have higher glass transition temperature than polypropylene? It's a gate question.
Polar interaction
Okay, how do you say polar interaction?
because chloride is polar than CH3.
Perfect. Polar interactions, as you said. So this the chloride ion, the chloride group, it causes polarity. So this polar interaction makes polyvinyl chloride have higher glass transition than that of the polypropylene. So which is having only CH3 group. Okay.
Okay, ma'am.
Yeah. So the glass transition of PVC is nearly 80, while that of polypropylene atactic is nearly minus 20. Okay.
Ma'am, what is atactic?
You have to say me. This was explained in the I think week one lectures with the tacticity,
I
atactic,
forgot about it.
isotactic, and syndiotactic.
I forgot about it.
Yes. So it depends on, see, for example, in case of your polypropylene, you have this, uh, you will have C, C, and then H, 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 CH3, right? That
Yes,
will
ma'am.
be your polypropylene, correct? So if this
Yes, ma'am.
CH3 So there's a long chain of this group, this propylene group, correct? In that long chain, if all your CH3 is 3, so it can be either on this side or this side, right? The CH3. So if it
Oh,
is on
yes.
completely one side, it is isotactic. If there is a alternate arrangement, syntactic. If there is no particular sequence in which the CH3 is placed, then it is atactic.
Okay, got it.
Yeah. Yep. Now let's go to question number 16. Butyl rubber is a copolymer of isobutylene and butadiene, butadiene and 1-butene, isobutylene and isoprene, isoprene and 1-butene.
Isobutylene and isoprene.
Okay, you're right. It's isobutylene and isoprene. This is the structure of your isobutylene, isoprene, and your butyl rubber. Okay.
Okay, ma'am.
Yeah, you will have some m units of your isobutylene and n units of isoprene. Okay. Um, okay, it's already shown. Anyway, you got the answer for this. So nitrile rubber is a copolymer of styrene and butadiene, styrene and isoprene, styrene and acrylonitrile, butadiene and acrylonitrile.
Uh, Butadiene and acrylonitrile.
Yeah, it's already shown in the
Okay.
answer. It's
Yeah.
butadiene and acrylonitrile. Where do you find this nitrile rubber? Very common, you would have seen.
I heard about nitrile gloves. Me.
Oh, yeah, perfect. Yeah, nitrile gloves. It's used in gloves. Yeah, if you are, very frequent in laboratories, you can see
Yeah.
these nitrile gloves.
Yes, ma'am. I'm a biotechnology student, so we are
You
somewhat
will be
familiar.
you will be
Yeah.
using nitrile gloves like left and right. You will be using it. Yeah.
Yes, ma'am.
Next, thermodynamically, two polymers with enthalpy of mixing delta H and entropy of mixing delta S form a miscible blend at a temperature T when delta H by delta S is equal to 0.5 of T, delta H by delta S is equal to P, delta H by delta S is 1.5 times of T, or delta H by delta S is equal to 2 times of T. Under which condition does two polymer form a miscible blend at a temperature T? Having enthalpy of mixing delta H and entropy of mixing delta S. This is again a gate question.
Yes. Um,
Huh? Hello?
yes, ma'am.
You were saying some answer?
I know, ma'am. Stay.
So what should be the case?
I don't know, ma'am. But I will go
Uh,
with option two.
Option 2, you're saying that is delta H by delta S is equal to T. Okay, so do you remember by any chance what would be the delta G? Gibbs free energy change for a miscible blend.
It is less than zero.
Okay. Now, how do you find the relation between delta H and delta S? You know that delta G should be less than 0. You're right. Delta G should be less than 0. Now, how should delta H and delta S be related then? Does delta G Gibbs free energy change have any relation with enthalpy of mixing and entropy of mixing? If it has
I-
any relation, what is the relation? Does it have any relation with the enthalpy and entropy of mixing? Gibbs free energy change? Is it related to these? What you said is
I don't know about that.
okay. Okay. But what you said is right. So Gibbs free energy change should be less than zero. So delta G of mixing should be less than zero. That is what is given. So for a miscible blend, delta G of mixing should be less than zero. That is what you see here. If delta G of mixing is greater than zero, then it is immiscible. Okay. So the delta G of mixing should be less than zero. So your delta G of mixing is related to your uh, enthalpy and entropy of mixing as follows. So delta G of mix is equal to delta H enthalpy of mixing mixing minus T into delta S of mixing. So that means delta H of mixing minus T delta S of mixing should be less than zero. Now you have to just do some manipulation of this equation. So if you just bring this to right hand side, so then delta H of mixing should be less than T delta S of mixing. And then bringing delta S this side again. So delta H of mixing by delta S of mixing should be less than T. So that is what. So in the given set of option, is there an option where delta H of mixing by delta S of mixing is less than T?
There is no option.
No option, is it?
5T.
Huh?
0.5T.
Yes. You're right. So among the given option A is the only one that satisfies the above condition. So delta H by delta S of mixing should be less than T. Here in the given option, they have given that delta H by delta S is equal to 0.T or 1.5 of T or 2 times of T. So if delta H by delta S is equal to 0.5 of T, that means it is only half of the T value. Right? That means
Yes,
it
ma'am.
is less than T. So that means for this set of options, option A is the right answer. For these two polymers to have a enthalpy of, for the two polymers to be, to form a miscible blend at temperature T. Okay? Hope you got it.
Got it.
Yeah. Now next. Monomers A and B form block copolymers when RA is equal to RB is equal to 0, RA equal to RB is equal to 1, RA is greater than 1, RB is greater than 1, RA is less than 1, RB is less than 1. Under which case A and B will form block copolymers. So you remember what is a block copolymer, right?
Yes, ma'am. Yes.
So what is a block copolymer first?
For polymer, which contain more than one type of monomer.
That is, that is a definition of uh, copolymer. Copolymer. In fact, it is not a clear definition of copolymer. In fact, in case of copolymers, there will be two monomers, and for example, in case of a homopolymer, for example, in case of PET, you have two monomers, right? Ethylene glycol and terephthalic acid. But it's not a copolymer, right? It's a homopolymer. Then what makes it different from a copolymer? What happens in case of copolymer is that each of these monomers, if for example, if it is a copolymer of two monomers, then each of these monomers have the capability of forming polymer by itself. For example, if there are two monomers, monomer A and monomer B. So monomer A can form a polymer of, having repeat units A, and monomer B can form a polymer which have repeat units only of B. In case of copolymer, what happens is that there will be repeat units of A as well as repeat units of B. Okay. But if you
Okay.
consider in case of a polyethylene terephthalate, ethylene glycol cannot form a polymer by itself. Terephthalic acid cannot form a polymer by itself. But when ethylene glycol reacts with terephthalic acid, it forms polyethylene terephthalate. Okay.
Okay, man. Yeah, I didn't notice this before.
Okay. Okay. Now, say me the answer for this. And now say me what is a block copolymer. In fact, I showed you the block copolymer when we were discussing the question on the gradient periodic, aperiodic copolymer and all.
Then block copolymer would be in different ratios.
I'll just show you what is a block copolymer. You could see the block copolymer. There is a block of complete sequence of orange followed by complete sequence of red. That means there is a block of one polymer followed by a block of another polymer. And this is how the arrangement will be. Okay. Uh, you could understand, right? There is a block of uh, one set of monomers followed by a block of another set of monomers. This is called as block copolymer. You got it?
Okay.
Whereas
Okay.
in
Yes, ma'am.
alternate copolymer, for example, you have alternating monomers. First orange, then red, orange, red, orange, red. That is how it goes. Okay. Now,
Yes, ma'am. Got it.
yeah. Now you have to say me.
Then in that case, RA will be lesser than RB,
Do you
lesser
remember?
than 1.
Uh, RA will be lesser than. So which option you're saying?
Option D, ma'am.
You're saying RA should be less than 1, RB should be less than 1. So do you remember what is RA and RB?
The ratio of rate constant.
Yeah, it's a reactivity ratio of rate constant. Yes. So what is the expression for RA?
K11 by K12.
Yes. So
And
and what is RB?
K21 by K22.
Is it K21 by K22 or K22 by K21? Okay.
K21.
Okay. Now, okay. Next, let's go to the next level. Uh, what does K11 represent? What reaction does K11 represent?
Reaction between the same monomer.
Okay. K12.
The reaction from between 1 and 2.
Okay. So you're saying K11 represents reaction between 1 and 1. K12 represents reaction between 1 and 2.
Yeah.
Okay. What does K22 represent?
The reaction between same monomer of the other type.
Okay. K21.
K21 means from the active center of 2 to 1.
Okay. Okay. So now these are all the points you got it. Right? Now say
Yes, ma'am.
me what should be the answer. If I have to form block of A followed by block of B. You want to think or shall I proceed with the answer?
And then I will go with option 2,
You're saying
equal to 1.
option 2. Okay. Now let's see. It's actually option C. RA should be greater than 1, RB should be greater than 1. So, for example, if you have to form block of A, right? A means K11 value should be higher than K12 value, right?
Okay.
That
Yes,
means
ma'am.
RA should be greater than 1. Similarly, if for forming a block of B, that is B continuously, then K22 should be greater than K21. So that means K22 by K21 should be greater than 1. Right?
Yes, got it.
Yeah. So RA should be greater than 1. So KA will be greater than KAB. So monomer will give more preference to join with monomer A. Similarly, RB should also be greater than 1. Monomer B gives more preference to join with monomer B. Okay?
I got it.
Yeah. So you said RA equal to RB equal to 1, right?
Yes, ma'am.
Okay. Under which type of copolymer formation this will be correct? You have the expression for RA, you have the
Yeah.
expression for RB. Now, for which type of copolymer formation RA and RB will be equal to 1? Whether it is, it's not definitely block copolymer. Is it going to be alternating polymer or random polymer or which type of polymer? Copolymer, sorry.
Then it will be random polymer, ma'am.
Yes, it will be random copolymer because A has equal preference for joining with A as well as joining with B. Similarly, B has
Yes, ma'am.
equal preference for joining with B as well as joining with A. That means uh, you tend to end up with a random copolymer. And when does RA equal to RB will be equal to 0?
Then it will be alternate polymer, ma'am.
Yes, that means A can preferentially joins with B and B preferentially
Only.
joins with A. Because
Yes, ma'am.
your denominator should be higher. If denominator value is very high, that
Very high.
means the fraction value is tending to 0. That means you end up with the alternative copolymer. Okay.
Yes, ma'am.
Yeah. So this is what just the explanation. This leads to block copolymer of A and B, forming a block of copolymer of A and blocks of A and blocks of B. This is the block copolymer structure. Now next question. A linear amorphous polymer has a glass transition of 10 degrees. At 28 degrees, it has a viscosity of 4 into 10 power 8 poise. Okay, the viscosity of polymer at its glass transition is dash into 10 power 13 poise. This is a great question. So what should you use? What equation
Uh,
should be
we
used? Yeah.
we will use mark ink.
Is it Mark-Wink? Does Mark-Wink give relation between viscosity and glass sensation temperature?
No, it only gives between mass and
Molecular weight and
molecular weight and viscosity.
yeah. So now what is the equation that is to be used? That equation was also discussed during our discussion in this session. There was also a doubt asked.
WLF relation.
Yes, you have to use WLF relation. Okay. So now they have given the glass transition temperature is 10 degrees and eta viscosity at 10 degrees. Sorry, they have given viscosity at 28 degrees is 4 into 10 power 8 poise. Now we have to find out what is the viscosity at glass transition. Okay. So we have the William Lander Ferry equation, which gives log of eta by eta g is equal to minus of C1 into T minus Tg by T minus of Tg minus C2. Right?
Yes, ma'am.
Yeah. Now, the value of C1 for this polymer, value of C1 is 17.44 and C2 is 51.6 in this case. Okay. So,
Okay, ma'am.
you have all the other parameters. You only have to find out what is eta g. That is the viscosity at glass transition. So, what is eta g? Calculate and see. Are you able to calculate?
Ma'am, I got it as 12,351.
12,300. Okay. Let's see. So it's so the right hand side expression becomes minus 4.5103 and then it's actually 1.295. There might be some this 10 power issue because they have already given it is 10 power 13 poise. So you have to find out what is the value. So you got something 12,000. Something it is 1 2, but some 10 power might be some issue. So it's actually 1.295 into 10 power 13 poise is the answer. Okay.
Okay, ma'am.
Yeah. So you're just incorporating eta, that is 4 into 10 power 8 by, so log of 4 into 10 power 8 by eta g, that is equal to minus of C1 is 17.44 into T minus Tg. So T is 28, Tg is 10. Here you are not converting it to Kelvin. And then you have, you know, the denominator T minus of Tg minus C2. So which is 28 minus 10 minus of 28 minus of 10 minus 51.6. So you will end up the value is minus 4.5103, and then rearranging, and you will end up with eta g is 1.295. The log goes this side, so it becomes 10 power minus 4.5103. So 4 into 10 power 8 by eta g is equal to 10 power minus 4.5103. And then if you just further take this eta g, you will get 1.295 into 10 power 13 poise. This is what is the calculation. Okay, next. The size of a coiled polymer chain in a dilute solution is Rg in a good solvent, Ri in an ideal solvent, and Rp in a poor solvent. So select the correct ordering of sizes. So will Rg be higher than Ri, which will be higher than Rp, or Rg be lesser than Ri, less than Rp, or Rp greater than Rg, greater than Ri, or Rp less than Rg, less than Ri. So where Rg is the radius of gyration in good solvent, Ri is in ideal solvent, and Rp is in poor solvent. What will be the?
It will be maximum in ideal solvent.
You're saying it will be maximum in ideal solvent.
I'll
Is it
go with
so?
option D.
Option?
D, fourth option.
You're saying Rp will be less than Rg, will be less than Ri. Okay.
Yes, ma'am.
Okay. Let's see what is the answer. It is actually Rg in the radius of gyration in the good solvent will be higher than that of the ideal solvent, which will be greater than that of poor solvent. It's because of this. In a good solvent, you will have more of a polymer and solvent interaction. The chain will be more of an expanded conformation. Okay. Oh, sorry. In more of an expanded conformation. That means your radius of gyration will be uh, higher, and it is related to your molecular weight to the power of 6.6. Whereas in case of ideal chain, what happens is this is also called as a theta condition, where we have the ideal chain where the macromolecules, it behaves as if there is no interaction with each other. And in this case, the radius of gyration is actually based on Gaussian chain approximation or random walk model. This random walk model was discussed in one of the previous week 2 lecture. And this radius of gyration is related to your molecular weight power 0.5. And finally, in a poor solvent, there will be more of polymer-polymer interaction, right? And it will tend to have more of a coiled state, ending up having a very low uh, radius of gyration, which is related to the molecular weight as m power 0.33. Okay, so that means in the very good solvent, the radius of gyration will be maximum, highest, followed by ideal solvent, because the molecule behaves as if there is no interaction with each other, and then followed by poor solvent, where it will be in completely coiled state. Okay.
Okay, ma'am.
Yeah,
Got it.
fine. Enthalpy of crystallization of liquid crystalline polymer is lower compared to semi-crystalline polymer. Why? Why does enthalpy of crystallization of liquid crystal polymer lower than that of the semi-crystalline polymer? What is enthalpy of crystallization?
The energy required to crystallize.
So the energy will be either absorbed or emitted during crystallization, right? So this enthalpy for liquid crystalline polymer is low compared to that of semi-crystalline polymers. Why? This was discussed in the liquid crystalline polymer lecture. Are you able to recollect anything?
The entropy below in say a liquid crystalline polymer.
Can you repeat it, please?
The entropy is lower in liquid crystalline polymer.
Which entropy is lower?
The translational entropy.
Translation entropy is lower in case of liquid crystalline polymer, is it?
I don't remember exactly.
Okay, now let's see what is the actual answer. So, in case of liquid crystalline polymer, it actually has higher translation entropy. Okay, whereas there will be an orientational order. Okay, so if you just look into this liquid crystalline polymer, there are these orientational. There is an order in the orientation, but see, once you have this crystal structure form, the orientation is kind of fixed. But still, you will be having translation and entropy. That is, this block can move between this region and this region. Similarly, this block can move from this region to this region. So, these can move still there, but the overall order of this kind of an order, right? This kind of a vertical order will remain same. Okay, so there is still a flexibility of the molecular motion. That means, so because of translational entropy, there is, since this mesogen can move between points in this within this order, that means there is some flexibility in the molecular motion, right? The molecule is still able to move and show some flexibility, correct?
Yes, ma'am.
Whereas if you consider a semi-crystalline polymer, you have the folded crystal chain. Okay, and in this folded crystal chain, once the crystal chain has folded and formed lamella and all, there will not be any kind of a motion. Okay, and only
Oh,
vibrations will be possible. So what happens? So the energy absorbed or dissipated during these vibrational changes will be very minimal, whereas during translation changes will be comparatively more. That means when you have to phase change from a crystal to melt, so there will be a larger energy associated in that process in case of a semi-crystalline polymer. Whereas in case of a liquid crystalline polymer, since there is some already kind of an energy transitions happening, the enthalpy of crystallization, that is from a crystal phase to melt phase or melt phase to crystal phase, whenever it is happening, the energy associated with that will be much lesser. You got it?
got it.
Now next. Silicon polyether copolymers are widely used as,
The surfactant,
yes, perfect.
surfactants.
Yeah, perfect. So silicon polyether, this is a structure of silicon polymer where you have this siloxane group, and this is the polyethylene oxide. So combination of these two you will end up with silicon polyether copolymer, and this is widely used as surfactant. Okay, and it has very wide application in different fields. There's a complete discussion there's a greater discussion in the lecture. Okay. Now,
Okay, ma'am.
in the copolymers lecture, there's a greater discussion of the different application where it is and how the surfactant, uh, behavior is being utilized in different kind of an application and how it is, exhibited. Okay. Now next. Polyethylene and polypropylene form an immiscible blend mainly due to entropy factor. Okay. Now answer the below question from GATE 2024. A suitable physical compatibilizer of a binary blend of polyethylene and polypropylene is it polycaprolactam, polylactic acid, or polyethylene block propylene, or polycarbonate?
Of third option.
Huh?
Third option.
Yes, you are right. It's polyethylene block polypropylene. That is the compatibilizer that is used for for blending polyethylene and polypropylene. Okay. Now, next question. Solve the following problem taken from GATE 2024. The propagation step of a free radical copolymerization is represented by the following possible reaction steps. So, where P1 is given by uh, active radical of M1 plus M1 gives M1 star. The rate constant is K11. P2 is M1 star plus M2 gives M2 star. And then P3 is M2 star plus M1 gives M1 star. And P4 is M2 star plus M2 gives M2 star. The rate constant for each of the reaction is K11, K12, K21, K22. Where M1 and M2 are two monomers and M1 star and M2 star are the active radicals of M1 and M2 respectively. Kij, I, j equal to 1, 2 represents the rate constant of each step as shown above. The reactivity ratios of M1 and M2 are expressed as R1 is equal to K11 by K12 and R2 is equal to K22 by K21 respectively. And the feed mole ratio F is expressed as F is equal to concentration of M1 by concentration of M2, where M1 and M2 are the concentrations of M1 and M2. The square brackets M1 and M2 are the concentrations of M1 and M2 respectively. The probability of reaction P2 is, what is the probability of reaction P2? Is it R1 by R1F plus 1 or 1 by R1F plus 1 or 1 by R2 plus F, or is it R2 by F plus R2? How do you start about this? First of all, what have they asked?
There's a probability of P2 reaction.
Probability of P2 reaction. So what is the P2 reaction?
M1 plus M2 gives M2.
So M1 star plus M2 gives
Yeah.
M2 star. So what will be the probability of this reaction? Right? So how do you go about it? Any clue?
No clue, ma'am.
Okay, let us solve this problem. So what is the insight from the question? So the insight we can arrive is that M1 star can react in two probable ways. Correct? M1 star can react with M1 to form M1 star, and M1 star can react with M2 to form M2 star. Right?
Yes,
Correct?
ma'am.
Yes. So M1 can react in two probable ways. One with M1 forming M1 star with rate constant K11, and two with M2 forming M2 star with the rate constant K12. Now, therefore, the total probability of M1 star reacting is sum of probabilities of reaction P1 and reaction P2. Correct? Because only two reactions
Yeah.
can happen with M1 star. So, the total probability will be sum of these two reactions, which will be nothing but 1. The total probability will be 1. So probability of P1 plus probability of P2 is 1. Correct? Now next.
Yes, ma'am.
Now what is the probability of reaction P2? So probability of reaction P2 is desired or favorable outcome by total outcome. Correct? So probability of P2 is, the favorable outcome is reaction P2 and the total outcome will be reaction P1 and reaction P2. Sum of reaction P1 and sum reaction P2. Correct?
Yes, ma'am.
Yeah. Now I have just written the expression again and I have written the reaction equations with rate constants again. So reaction P2 can be expressed by rate equation. Correct? So what is the rate equation for reaction P2? How do you write the rate equation for reaction P2?
Uh, Concentration of uh, reactant by concentration of product.
Is it? So the rate equation for reaction is written by concentration of, sorry, the rate constant into concentration of the reactants. Okay. So it is K12 into M1 star into M2. Similarly, for reaction P1, we can write the rate expression as P1 is K11 into M1 star, concentration of M1 star into concentration of M1. Right? Now, a probability of reaction P2 is, we already have the expression P2 by P1 plus P2. That means the rate equation of P2 by rate equation of P1 plus rate equation of P2. So that is nothing but K12 into M1 star into M2 by K11 M1 star M1 plus K12 M1 star M2. Right? Now, what we have to do is that we could see both in numerator and denominator there is M1 star. So we are just taking the M1 star out and cancelling it. You will end up with this expression K12 concentration of M2 by K11 concentration of M1 plus K12 concentration of M2. So dividing numerator and denominator by K12 concentration of M2, you will end up with probability of reaction P2 is 1 divided by K11 by K12 into M1 by concentration of M1 by concentration of M2 plus 1. So where K11 by K12 is equal to nothing but your reactivity ratio R1 and M1 by M2 is nothing but concentration of M1 by concentration of M2 is nothing but your feed ratio. Right? So if you substitute that, you will end up with 1 by R1 into F plus 1. Probability of reaction P2 is 1 by R1F plus 1, which is nothing but your option B. Okay? Hello?
Okay, ma'am. Perfect.
Okay. Yes. You just have to just substitute the reaction rate equation and then just solve it in the probability expression to find out what's the probability. That's it. Next. So these are some of the questions posted in earlier sessions in the forum. Okay. So one question was why silicone is commonly used as a coating agent, whereas silicone is an elastomer like rubber. What makes silicone restrict its application only in limited areas? Why not as a tire? What is the reason and how to make silicone suitable for various applications? This was posted by one of the students, Shweta. This is not posted in the current forum. Okay. This was posted in earlier forums when this course was given in earlier years. Okay. Which was July November 2022 session. So the answer is that, so you are able to understand the question, right? The student has asked why is silicone commonly used as coating agent only, whereas but silicone as such is an elastomer like similar to that of rubber. And what makes silicone restrict its application only in limited areas? Why not in tires? And what is the reason and how to make silicone suitable for various applications is what the student has asked. So what was the answer given by the professor is that application of the material is not based on class of behavior, one class of behavior alone. It's a typo error. It's not one class of behavior alone. Hence, just because silicone is a rubber-like material, it does not mean that it can replace other rubber-like materials in any application. A material can be used based on combination of several properties. So, also cost is an important factor. And silicones in general are very expensive. Okay, this is what is the answer. Okay, it's not just because of one property the entire behavior is decided and application is decided. Several properties play in combination for the end application of a material. And also one of the another important factor that is to be considered is cost for restricting applications. Okay, that is what is the answer. Okay.
Ma'am, so silicon is a amorphous or crystalline.
I'm really not sure because there are different silicone polymers. Okay, the polydimethyl siloxane itself, you can form the different combinations of silicone polymers. It's uh, with silicone. That is silicone unit is SiO unit, siloxane unit. So with that, different types of combinations can be formed. So
Okay,
we really cannot say whether that particular silicone is amorphous or crystalline. Okay.
okay,
Only thing is that in case of other polymers which we generally restrict to is we say which we commonly refer is based on CC linkages. Correct. The backbone is based on you even have this silicon polyether.
It's the copolymer.
So 1 second. I think I went. Yeah, it's a copolymer. 1 second, please. I'm just going to the slide. So in case of the carbon based polymers, the backbone mostly consists of carbon, right? CC bonds. Whereas in case of silicon, and then you also have some other materials like oxygen or sometimes nitrogen or all those things also is possible. In case of silicon, the backbone is formed by a siloxane group, SiO group. Okay, and different combinations can be there in the side chains. Okay.
Okay,
So similar to your carbon based polymers, silicon based polymers can also be because if you see the valency of carbon and silica, it is 4, right? So there will be other side groups also, and polymerization also, different kinds of side groups can be there. So all these multiple parameters, it actually decides whether it can form a crystalline polymer or it can it can form a semi crystalline polymer or it can form an amorphous polymer. Okay.
okay, got it.
It's not just because see, for example, with carbon based itself you have polyethylene, polypropylene, polyvinyl chloride. Similarly, you will have silicone based also, different kinds based on the the side groups and the main link also. Okay.
Okay, ma'am.
Yeah, it's not like a single compound. Okay. PET means polyethylene terephthalate. Silicone is not just like that. It is very similar to your carbon-based polymers, what you see. So that is also of very wider scope. I mean, very wider variations. Okay. Now, for example, here you have CH3, CH3. There can be some other group also here. So that will form a different, silicone polymer. And you will end up with different kind of properties that will and different kind of segmental mobilities and other things, so that will restrict its structure from forming a crystalline structure or forming an amorphous structure. Hope you're clear, right?
Yeah, got it.
The next question that was asked is, why not alternating copolymer could be a homopolymer as it contains same repeating unit throughout the chain? This was asked by a student called Uday Kumar. Okay, so what was the answer? So before seeing the answer, what do you think about this? Why not alternating copolymer could be called as a homopolymer? Because it has same repeating unit.
Because variation of properties might be there.
No, we just had some discussion on copolymers. That is one of the major reason. See what it is.
Okay.
Let's see what it is. So alternating copolymer means alternate of two different monomers. You have PQ, 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 right? And as I discussed, in case of copolymers, the individual monomers can itself polymerize to form a polymer. Correct?
Oh,
So
yes.
P
Oh,
can form a polymer, P, 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 P. And similarly, Q can form a polymer, Q, 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 Q. With the repeating units of P and Q respectively. Right? Whereas if you
okay,
consider
okay.
homopolymer, uh, homopolymer of two monomers P and Q, for example, in the case of polyethylene terephthalate, just now we had the discussion, right? It cannot, ethylene glycol and terephthalic acid cannot separately form a polymer by itself. Only if it reacts together, it forms a polymer. So, therefore, a polymer with repeat unit of PQ is called a copolymer of P and Q. This is what is the discussion. This is the same discussion we had just few minutes back when we were
Okay.
discussing on copolymers, right? So
Yes,
we
ma'am.
have to keep in mind the definition of what is a copolymer. Next, whether orientation of fibers or any particles into polymeric system is controllable. If so, how? And this question is was posted by a student called Shweta. Again, these are all questions posted in the earlier forum. I think in the current forum, one student, I think Revati, she asked she highlighted one issue which was on the lecture on biopolymers, which was the video was it was incomplete. Now that has been rectified, and the complete video lecture, including on xanthan gum and natural rubber, everything is put up. There was one more question which we will answer it uh, in the following week, and we will also have the discussion of the same in the next live session. Okay, now,
Ma'am, is it in the week one videos?
yeah, it was the week one video. It was lecture 4
Okay.
week one video on biopolymer.
Okay, ma'am.
Yeah. Now let's come back to this question, whether orientation of fibers or any particles in polymeric system is controllable. If so, how? So orientation is affected by flow and deformation during processing. So due to shearing, a rod-like object can be oriented in a flow direction. So that means there is a possibility to control the orientation based on what type of processing and what is the shear rate being used and how much is the deformation. So based on this, the orientation can be controlled and it can have an effect. Okay, that is what was the answer. I'm just trying to highlight these questions so that you also come to know that you can also think of these questions. Okay, yeah, that's it. So is there any other doubt?
Ma'am, that's it. The session was very helpful,
Pardon, I didn't get you.
and this session was helpful.
Okay, fine. So I think last time you asked for some more of numericals. I think I included numericals possible what I could be able to include.
Ah, yes,
I'll try
yes. I
including
could
much
see
more.
more numerical.
Okay, I'll try including as much possible for the following sessions as well. Okay. Yeah.
Okay,
So
ma'am.
yeah, if there are no other doubts, then we can officially end the session.
Okay, ma'am. Thank
Yeah.
you very much.
Yeah. Thank you.